Hi there. Okay, welcome to lecture 8 of Fox. And we're gonna be talking about proofs with recursive objects. Okay. Now let's recap where we were from last time. Okay. So we've talked about recursion. So we've introduced recursion, recursive programs, recursive sets, and recursive structures. In particular, the rooted binary tree, recursive definitions of sets like the natural numbers. So recursion is a very important, powerful technique, but you have to be careful with it. And one of the ways to be careful with recursion is to always prove that your recursion or your recursive set does what you expect it to do, does what you intended it to do. Okay? And so we're going to be talking about how do we prove things about recursive objects. Okay? So it is actually a good time now to go back and reread chapter 4, that's about proofs, chapter 5 and 6 very carefully about induction, because recursive sets and recursion in general relies a lot on induction in order to give us the sort of power tool, this sort of hammer that allows us to conclude that our recursive object does what we want it to do. Okay, so today we're going to be talking about proofs with recursive sets, the kinds of things we would like to prove and how to go about proving them. In particular, we're going to introduce this concept called structural induction. Okay, so induction is everywhere. It's going to be with us for a long time. Okay, so get good at it. You'll never regret it. Okay. Now, I also want to mention that even though we have this new fancy technique called structural induction to prove things about recursively defined objects, recursively defined sets, structures, and so on and so forth. It's just induction. Actually, it's a form of strong induction in disguise. But it's convenient to have, sort of a reformulation, a summary of how strong induction is applied to recursive objects, and we call this method structural induction. But it is just induction. There's only induction. Induction is the king. Okay. We'll also, prove one or two things about rooted binary trees, and to do so, we will use this technique called structural induction. Okay. So, as usual with all things math, let's go to the board. Okay, so let's start with a basic recursive set and see, what kinds of questions would we like to ask of such recursive sets. Okay, so I'm going to define a set A. Okay, recursively. So, A, is a recursive set. And as usual, I'm going to tell you something that's in A, so the base case. So let us suppose that, 0 is in A. So this is the base case. So a little bit of review. So this means we can start constructing our set A. It has 0. Okay. And now I'm going to tell you how to construct new elements. So the constructor case. Okay. So if x is in A, then x plus 4 is in A. Okay. So from 0 being in A, we can conclude that 4 is in A, 0 plus 4. And then we can conclude that 8 is in A, 4 plus 4, and then 12, and then 16, and so on. Okay, so this ... before, we sort of frowned upon it. Now we have a formal definition of this set. Earlier on we saw that there are ways to define sets with variables. Okay, so here's a new way to define sets, recursive definitions of sets. Okay, and always there's the minimality clause. Nothing else is in A. Okay. So questions that we might like to ask of this set A. So question 1. What is in A? In other words, does everything in A have some property? Okay. And so for example, if something is in A, is it necessarily even? So x is in A implies, x is even. Okay. So this is one thing we might like to know. So this is basically asking the question, what is in A? Does everything in A have some property? In particular, if you're in A, are you even? Okay. And in this case, just by inspection, you can see that this is true. Okay, so what is in A? Anything that's in A is even. Another kind of question might be, okay, so we've sort of understood that, if you're, we sort of understood that if you're in A, then you're even. Another interesting question is, well, is it then the case that, everything that's even is in A? So this is not really asking, what is in A. So does every object that is in the set A that we recursively define, does every object have some property? A different question. Is everything with a particular property in A? Okay. So, is everything with some property in A? So what we're asking here is a question of the form. For example, we could ask, so we know that everything in A is even. Is everything that's even in A? So if X is even, then is X in A? Does that imply that X is in A? So this is, okay. So, does everything with some property belong to A? Now, it's very important to emphasize, that these are two very different questions. Okay. Here we're asking about what's in A. Here we're asking about all objects with a certain property. So we're defining some set in another way by the set of objects with some property, and we're asking whether all of those are contained in A. Now, to emphasize the difference, let me give you an example from, the real world. So every leopard has 4 legs. Okay, well, assuming they haven't gotten a leg chopped off or anything. Okay, but, you get the idea. So we've defined a set of leopards somehow, okay, and everything in this set of leopards has 4 eggs. Contrast that with every animal with 4 legs is a leopard. You see, that's the difference. Okay, so everything that's in my set of leopards has a property. Everything with a particular property, so that's a different set. In theory, it could be a different set. Okay, and we're asking whether this different set is a subset of leopards. So everything with 4 legs is a leopard. Here we're asking whether the set defined as leopard is a subset of everything with 4 legs. Okay, so it's 2 different things. So here we're asking, so sort of, if you define the even numbers, if we put this in mathematical form, if you define E as the set of even numbers, okay, here we're asking the question, is A subset of E? Here we're asking the question, is E a subset of A? 2 very different questions. And remember, long time ago, we talked about the definition of the subset relationship as an implication. In this case, this is false. Okay, and that also underlines the difference between these two, because 2 is even, but 2 is not in A. So this is false. Okay, and just like this, every leopard has 4 legs. True. Every animal with 4 legs is a leopard. False. Okay. So, 2 types of questions we might like to ask about about a recursively defined set. Okay, and we're going to focus a little bit on structural induction. Okay, and structural induction is a method for proving the first question, proving your answer to the first question. Okay, so in this case, we say it's true that everything in A is even, but how do we prove it? Okay, so here we can use structural induction. The method for proving this first kind of question. What is in A? Answering the question, what is in A? Does everything in A have some property? Okay, you don't use structural induction to prove the second kind of property. Even though the second kind of question is also an important question, you use a different kind of induction usually, and we'll discuss some methods for proving this kind of proving things about these kinds of questions. Okay, so how do we prove this? It's another kind of induction, but not structural induction. So we're mostly going to focus on structural induction. Okay, and I want to give you a high-level picture for how structural induction works. Okay. Okay, so structural induction, bird's eye view. Okay. Think of inheritance and ancestry and how traits pass from one generation to the next, and in that sort of process is the essence of structural induction. Okay, so let me illustrate. orcs. Okay. You know, just some fictitious character. Okay. And I'm going to tell you that, you know, so orcs, just like humans, they mate, the pairs of them mate, and they have children, and, you know, this whole process continues generation after generation, and you get, you know, you started with 2 orcs, so you started with 2 orcs, and then this happens for centuries and millennia, and now you have, you know, 4 billion orcs. Okay. So, what I'm going to tell you this. Okay, you started with 2 orcs, and they both had blue eyes. Okay, good. Now I'm going to tell you something else. Okay, I'm going to tell you that, you know, when 2 orcs mate to have a child, okay, and, you know, now, you know, there may be, you know, different mating rituals and whatnot, and, you know, I'm not making any sort of restrictions on which 2 orcs mate, but what I'm going to tell you is that when 2 orcs mate to have a child, okay, if they both have blue eyes, the child will have blue eyes. So if 2 orcs mate to have a child, if the blue, or if both have blue eyes, then the child has blue eyes. Okay, so in other words, this is a trait that is passed down from parents to children. If both parents have this property, blue eyes, so in words, okay, so think of, you know, you have orc 1 and orc 2 who are about to mate. Okay. And if orc 1 has blue eyes, and so orc 1 and orc 2 mate and produce, you know, orc 3, which I could write maybe as little O3 for a baby orc 3. Okay. So if O1 has blue eyes and O2 has blue eyes, so O1 and O2 have this property. Okay, if these 2 hold, then O3, the little baby orc created, O3 has blue eyes. Okay, so, you know, imagine that we have, you know, we have recursively defined this set of orcs, which starts with the primordial ancestors, these first 2 orcs, and then, you know, you have your constructor rule, which is that if any 2 orcs come together, they can mate and produce a child. Okay, so that's a way of getting new orcs into my set. Okay, and now I have a property of orcs which is called blue eyes, and if 2 orcs mate and they both have blue eyes, which, you know, if 2 orcs mating is part of the constructor rule, so if 2 orcs who mate to produce a child, and if they both have blue eyes, the child has blue eyes, okay, then the question we're going to ask is, what can we say about all the 4 billion orcs today? Okay, in particular, do all the 4 billion orcs today have blue eyes? Okay. What can we say about all the 4 billion orcs today? Okay, and intuitively you can sort of convince yourself that, well, this is just inheritance, right? If a trait is passed, you know, without any change, you know, 100% accurately, if a trait is passed from parents to children, then all the children will have that trait. Okay, providing that the parents have that trait. Okay, and then the children of those children will have that trait. In other words, when could a green-eyed orc have popped up? So when could a green-eyed orc have popped up? Because the primordial ancestors had blue eyes, and so if a green-eyed orc popped up somewhere down the road, well, you can consider the first green-eyed orc that popped up and ask, well, if that's the first green-eyed orc that popped up, well, then the parents were blue-eyed, because that's the only way to create a new orc. And if the parents were blue-eyed, then how did this green-eyed orc pop up? It's not allowed. You're violating the rules of inheritance. Okay. And so this sort of intuition of inheritance and, you know, how traits are passed from one generation to another is the essence of structural induction. Okay, so let me summarize structural induction. Structural induction. Induction. Okay. So here's the basic idea. You prove, you show that your primordial ancestors have some property. In this case, blue eyes. And in this case, I didn't show it. I just told you. That's a fact. It's true. Can't argue with the fact that I tell you it's true. I tell you it's true. It's true. Okay. So you show that the primordial ancestors have some property P. Okay. You just show it. Okay. And then you must show, if you can show, that this property P, this trait, this property P is passed from parents to children. So this property P, the property P is passed from parents to children. Okay? If you can show that the primordial ancestors have this property, the first two orcs, and if you can show that whenever parents get together to produce a child, the property is inherited without flaw. Okay. Then the principle of structural induction says that you can conclude that all of your, population, the entire population, conclude that the entire population has the property P. Okay. Now, we could prove the principle of structural induction. It's just a straightforward application of strong induction. We could prove it from the well-ordering principle. There are many ways to prove it, but I'm going to, rely on your intuition to take this as, yeah, it makes sense, and you can see the text, in chapter in chapter 8, gives a much more thorough discussion of how we would, go about proving this. Okay, but instead, let me just show you how does this apply to recursive sets. Okay, recursively defined sets. Well, who are the primordial ancestors? Those are your base cases. Okay, so the equivalent of the primordial ancestors are the base cases in a recursively defined set. So these are the base cases. Base cases. Okay, and what is this, this concept of a property? Well, that's a predicate. So you make a claim. So the input will be a member of your set, okay, an element of your set. That's the domain of the predicate. And the predicate makes some claim about that input, that element of the set. For example, has blue eyes or is even. Okay, so this property P, that's what we call a predicate. Okay, and now what's this notion of from parents to children and so on and so forth? Well, we have to go back to the, the way in which a recursive set is defined. Okay, and there are base cases, and then there's a constructor rule. Okay, so in a recursive set, there's a constructor rule. Okay, and what does a constructor rule do? It says that, if some object is in your set, X is in your set, let's say set, then, Y is in your set. Well, there's no reason to limit constructor rules to just being able to construct new elements from one element. Okay, so we can generalize the constructor rule. So in the example with the set A, one element produces another element, but you could have multiple elements like a pair of, orcs, i.e. the parents. So you can have multiple elements, constructing or producing, a new element. So we could have a constructor rule like, if X and Y are in your set, then, X plus Y is in your set. Perfectly valid constructor rule. Okay, and in general, what we say is that on the left-hand side are the parents, and on the right-hand side are the progeny or the children. Okay, makes sense. These guys got together and produced via the constructor rule these guys. So that's the notion of parents and children. And what we're saying is that if the property P holds for the parents, okay, then it holds for the child created. What that means is that the constructor rule preserves the property P. Okay, and important, it's an if-then. It doesn't have to produce children with the property P unless all the parents have the property P. So providing that all the parents have the property P, the constructor rule has to preserve the property P. Okay. And then the principle of structural induction comes and tells you, bam, your whole set has the property P. Okay. So you have to prove it. You have to prove the property P for the base cases, and then you have to prove that the constructor preserves the property P. And now we're going to do lots of examples of this. Okay. Starting with the set A. Okay. So let me erase. You know, the super duper speed erase. Okay, so, you know, the formal justification of structural induction is through strong induction. And you can read all about that in the text. Our goal is to do loads and loads of examples so that you get comfortable with the mechanics of structural induction. So we'll illustrate in many different, you know, settings. Now, you know, the intuition is, you know, probably enough to justify structural induction at this point, which is that, you know, this notion of inheritance and how traits are passed. If the primordial ancestors have some property and procreation preserves that property, the word preserves is important, preserves that property, okay, then the whole population has that property. So let's start with this set A. Remember, we defined this set A, you know, so it's a recursive definition. So 0 is in A, and the constructor, if X is in A, then X plus 4 is in A. Okay, so what is A? It's 0, 4, 8, 12, 16, and so on. Okay, so we want to show, now we're going to use structural induction to show that everything in A is even. So everything in A is even. Okay, and there are two steps. The first thing is you must show that the primordial ancestor, the very first, you know, elements in A have this property. In other words, the base cases have this property. So that's the base case of your structural induction. And so we need to go to the base cases of the recursive definition, and there's only just 0. So we need to show that, you know, even is a property of the base case, so the primordial ancestor, and 0 is even. And that's clearly true, so check. So we've shown the base case. We've shown that the primordial ancestors of this recursive set satisfy my property, which is evenness. Now, okay, so this is the induction step. Okay, show that the way you get new objects, so the procreation process, preserves the property. Show that procreation preserves the evenness property. Okay, now how do we show that the procreation process preserves it? So it means that, you know, so you have to look at the constructor rule, okay, and, you know, you look at the constructor rule and preserves means that if you started with that property remains, okay. So we have to show that for the constructor, okay, if you start with the property, then the property is preserved in the offspring. Then the property is preserved in the child. Okay, so if you start with the property, i.e., you know, the parent has the property, then it's preserved in the child. So let's see. So we have to, in the constructor rule, we have X that is in A, okay, implies X plus 4 is in A. So X is the parent, okay, and the new object that's created is X plus 4. So this is the child. So we have to show that if the parent has the property, which is even, if X is even, then X, the child, has that property. X plus 4 is even. Okay? And to prove this, we can use a variety of methods. Let's just use a direct proof. If X is even, so X equals 2K, that implies that x plus 4 equals 2k plus 4, which is equal to twice k plus 2, which is twice a multiple, which is twice an integer. So this is even. So that means that x plus 4 is even. And so this evenness property is preserved by the constructor. So evenness is preserved. And so by induction, okay, every element of A is even. Is even. End of proof. And now, even though technically this is structural induction, we still say by induction because induction is induction. All inductions are equivalent. Okay, and you know, if we want to sort of justify structural induction, we do it through strong induction. So this is it's essentially the case that structural induction is strong induction in disguise. Okay, so it is induction. Okay, now let me emphasize. Okay, so here are the mechanics. You have to prove the base case. So you have to prove that your property, whatever you're trying to prove for every element of A, you have to prove that the base case satisfies that property, and then you have to prove that the constructors preserve the property. Preserve means that if you start with parents that have that property, so all the parents must have that property. So if you start with parents that have the property, then it must be the case that the child has that property. So the parent produces a child. If the parent has the property, the child has the property. Okay, now let's look at that other question quickly, just to be complete. Okay, so is every even number in A? The answer is no. For example, 2 is not in A. Okay, and let's ask another question, which is true. Is every non-negative multiple of 4 in A? Is every non-negative multiple of 4 in A? Okay, and the answer is yes. Okay, and in fact you can prove that A equals the set of all non-negative multiples of 4. So we proved that every element of A is even. So now I encourage you to use structural induction to prove that every element of A is a multiple of 4. Okay, so prove that every element of A is a multiple of 4. And now I'm going to do the reverse question. Is every multiple of 4 in A? Just to illustrate how we answer that second question. Okay. So the answer is yes. And now what's the proof? Okay, the proof is by contradiction. Okay, so suppose not. Suppose it's not the case. Suppose not. Then by the well-ordering principle, there's some smallest multiple of 4 that's not in A. By well-ordering, there is some smallest multiple of A, some smallest multiple of 4 not in A. So let's call that smallest multiple of 4 x star. Okay, x star is not 0 because 0 is in A. So x star is greater than 0. Okay, so that means that x star is greater equal to 4. And it's a multiple of 4. Okay, that's not in A. Okay. Then let's consider x star minus 4. Well, this is greater equal to 0. Okay. And x star minus 4 is a multiple of 4 because x star is a multiple of 4. So this is 4k minus 1. So this is 4 times k minus 1. Okay, so this is a multiple of 4. Okay. And therefore, x star minus 4 is in A. Now this is the important, conclusion. Okay. So it's a multiple of 4. Okay. Now why do we know that it's in A? Okay. Because it's greater than or equal to 0, so it's a non-negative multiple of 4, and it's smaller than x star, so it must be in A. Why? Because x star is the smallest one that's not in A. So by the well-ordering principle, this guy is the smallest, and since this guy is strictly smaller, that means that this must be in A, because x star is the smallest multiple of 4 not in A. So this is a multiple of 4. This is a multiple of 4. It's smaller than x star. Therefore, it must be in A, because otherwise x star wouldn't be the smallest guy that's not in A. Okay. So this means that x star minus 4 is in A. So x star minus 4 is in A. But then the constructor says that x star minus 4 plus 4 by the constructor, x star minus 4 plus 4 is in A. But this is just x star. And that's a contradiction, because we just saw that x star is the smallest guy not in A. How can it be that x star is the smallest guy not in A, but then it's also in A? That's fishy. Fishy. Okay. And therefore, suppose not was false. That means that every multiple of 4 is in A. End of proof. Okay. That's just to show you how we answer the other kind of question. It's a much more complicated question to answer. It's usually a proof by contradiction, where you say, okay, let's consider this, all things, of the kind you're interested in. In this case, multiples of 4. Well, if, they're not all in there, then there's some smallest guy who's not in there. Then you work around, you explore, and get a contradiction. Okay, good. Okay, so let's do another example. I'm going to define a new set, M. Okay, so we're going to define a new set, M, just to show you the wide variety of things we can apply induction / structural induction to. So let's define the set of strings. So M is a set of strings. Okay, now, so I'm going to tell you something that's in M. Nothing is in M. Okay, the empty string. The empty string is in M. So this is the base case. Okay, and this is the empty string. So the primordial ancestor of M is the empty string. Everything in M is created ultimately from nothing, from the empty string. It's kind of like the Big Bang. Okay, we've got nothing, and then the Big Bang creates everything. Nothing creates everything. Okay. Now, how do I get strings that are in M? Okay. From strings that are known to be in M. So the constructor. Remember, we always have the third rule that nothing else is there. Okay, the minimality rule, the minimality clause. Okay. So, if x and y are in M, so at the moment we only know that epsilon is M, so x and y are both epsilon. Okay, but if x and y are in M, then, okay, now this is interesting. I'm going to put parentheses around x and y. So these I'm going to create strings of parentheses. So I'm going to put an opening parenthesis around x and a closing parenthesis around y. Opening parenthesis to begin. I'm going to surround x in an opening and a closing parenthesis, and then I'm going to add y. Okay. So if x and y are in M, then this strange thing is also in M. Okay, so let's see, what's in M. Let's construct the strings in M. Okay. So we know that M starts off, the primordial ancestor is epsilon. Okay. Okay. Now, let's apply the constructor with epsilon. So x and y are in M, so epsilon and epsilon are in M, so I can replace epsilon here. Okay, so epsilon is nothing, so that puts an open and a close around the first epsilon, and then you append the second epsilon. So we have, from this guy, that creates an open epsilon, a close, and an epsilon. But since epsilon is nothing, this is the string of two parentheses, which is open and close. Okay. Interesting. Now we have a second object that's in here. Okay. So we can set either x equal to that or y equal to that. Okay. So from this guy, now what can we get? We can get, so let epsilon equal x, so we can get epsilon, open, close. Okay, so if I set epsilon equal to x, if I set y equal to this guy, then I get open and close. Okay, so that means that this thing is in my set M. Okay, so I have this guy. Interesting. Okay, and let's see what else I can construct in M? Well, let me use this guy, and instead of making x equal to epsilon, let me make x equal to this guy. So I'll place an open and a close around this guy. Okay, I'll let y equal epsilon, so epsilon. But that's nothing, so I got another guy in here. An open, and a close, and a close. Okay. You see, I'm constructing strings which consist of open and closed parentheses. Okay, and now it would be very interesting to try to guess what kinds of strings I'm constructing. So I encourage you to play, and see what else do you get. Okay. I claim, for example, that the following string is in here. So I claim that, you know, open, close, open, close. I claim that that guy is in here. Okay, so what's the derivation? Okay, so let's see if we can come up with a derivation. So epsilon is clearly going to, we've already derived this guy. So that gives me this guy. Okay, with x equals epsilon and y equals epsilon. And then I can get that guy with x equals this guy, the one I just derived, and y equals epsilon. So that gives me, you know, this. Sorry. With x equals this guy, and y also with x equals epsilon. Sorry, yeah, this guy here with x equals epsilon, and y equals this guy. So order matters in this constructor. Okay. With x equals epsilon and y equals this guy, I get this guy here, which is, you know, open. I put an open and a close around x, okay, and then I produce y. Okay, and you see now I've built the inner part here. So if I use this guy as x, so x equals, you know, this guy, and y equals epsilon. So what that's going to do is it's going to put an open and a close. It's going to put an open and a close around. It's going to put an open and a close around x, so around this guy, and then produce y, which is nothing. So I get an open and a close around x, which is an open, close, open, close. Okay, and there I've derived this guy. Okay, that proves, okay, so such a derivation proves that this guy is in my set M because I started from the, you know, the primordial ancestor and I applied the constructor rule successively, okay, and ultimately I end up deriving what I wanted to derive. Okay, question, what about this guy? Okay, open, close, close. Okay. Is that guy in my set M? No. Okay, it's not in my set M. But now the question becomes, how do I prove it? Is it easy to prove? Okay. How would I prove it? That's going to cause some, you know, uncomfortable thoughts because, you know, when you think about how to prove that this guy is not in the set, you realize that you need to show that there's no possible derivation, okay, that can produce this guy. And how am I going to check every possible derivation? Complicated. So I'm going to show you an alternate way of proving that this guy is not in the set. And the high-level philosophy is figure out some property that every string in your set has. Okay? Just like being even. Okay? Use structural induction to prove that every element in your set has that property, and then show that this string violates that property. So since we've shown that every string has that property, and this violates that property, then this cannot be in the set. Okay. So let's try to see, what properties do these strings have? Okay. So what properties do the strings of parentheses in M have? Okay, now the obvious thing that seems to be going on here is if you look at the number of red and black, so if you look at the number of open and closed parentheses, they match. There's an equal number of red and there's an equal number of red and black parentheses. We call such a string of parentheses balanced whenever there are an equal number of both. Okay, so balance. That's a property of a string of a string of parentheses. Balance. Okay. Equal number of open and close parentheses. Okay. There's another much stronger property, much stronger than balance, that these strings have. Okay, what's that property? Well, let's look. You know, if you think about arithmetic expressions, you know, you always, whenever you close a parenthesis, you must be closing something that was previously opened. So you never try to close something that was not previously opened. So we can match every closing parenthesis with some opening parenthesis. Okay, so that's another property of a string of parentheses. They can be matched. Okay, what does that mean? That means that every every closing parenthesis, that guy, can be matched with a corresponding opening parenthesis. Okay. Now you can't match, you know, a red close to more than one opening. Okay, so you create distinct pairs of opening. So opening and the corresponding guy that closed it. So opening and the corresponding guy that closes, opening that and the corresponding guy that closed it. In fact, how would we formulate that mathematically? Mathematically, the way we would formulate that is we would say that as you go from left to right in this string, you can count up the number of open parentheses and count up the number of closed parentheses, and the number of open will never be less than the number of closed. Okay, that's a formal way of saying that. But I don't want to get into the details. We sort of intuitively know what it means for the parentheses to be matched from arithmetic. Okay, so these are two properties. I claim that every string in my set M has these two properties. I'm going to prove using structural induction that they have balance. It's an exercise for you to prove that they're all matched. Slightly harder. Okay, so proof of balance. Proof of balance. Proof of balance. Well, we use structural induction, the same philosophy. Okay, so base case. Okay, the primordial ancestors. Okay, so the primordial ancestors. Well, there's only one primordial ancestor, which is epsilon. Epsilon, and it has 0 opening and 0 close, so it's balanced. Is balanced. Boom, check. Okay, so the property that I'm trying to claim for every element in M is this property of balance. Okay, and the primordial ancestor has this property of balance. Now, I need to show that this constructor rule that generates a child from parents, I need to show that this constructor rule preserves balance. Preserves balance. Okay, so I need to show, so the induction step. Show that the constructor rule preserves balance. Okay, and I'm going to underline the word preserves. I keep emphasizing the word preserves. So it's important to understand what it means to show that it preserves balance. You only need to consider the case that your parents have balance. Okay, and it's only in that situation that the constructor has to preserve balance. So it's kind of like the induction step in regular induction. You assume that the parents have balance, and you now must show that the children have balance. So suppose, so there's only one constructor rule. So suppose x and y have balance. This property called balance. Now we need to show, so the two parents have balance. We need to show that the constructor produces a child with balance. Need to show x, y has balance. And it's sort of obvious because there's the same number of opening black and closing red parentheses in x. There's the same number of opening black and closing red in y. Okay? And you've just added one of each. Okay? So you've increased the number of opening black by 1, and you've increased the number of opening red by 1. So, so the number of opening equals 1 plus the number of opening in x plus the number of opening in y. Okay. The number of closing equals 1 plus the number of closing in x plus the number of closing in y. Okay. But since these two are equal and these two are equal, then the top sum and the bottom sum are equal. Okay. So these are equal, these are equal, these are equal, and so when you add these three things, it gives you the same result as adding those three things. So these two are equal, proving that the child has balance. Therefore, the child has balance. And that's it. That's the end of the structural induction proof. Because we proved that the constructor rule preserves balance. By induction, every element of M has balance. End of proof. That's the proof mechanics for structural induction. Okay. So just like the orcs. So I just want to emphasize this. Just like the orcs. Okay. Epsilon is balanced. The first two orcs had blue eyes. Okay. And when two orcs get together to produce a new orc, the resulting child, if the two orcs had blue eyes, the resulting child has blue eyes. It's exactly the same. So the entire population that's in M now has blue eyes, i.e. balance. Okay. Okay. Let's consider some more examples. Okay. More examples. By the way, so immediately now we know that this guy is not in M. Why? Because it's not balanced. One opening, two closed. Okay. But let me show you a string of parentheses that is balanced. This guy. So that's balanced. So we might ask, is that guy in my set of parentheses? And that, you can try all kinds of derivations you want. You'll never be able to produce this guy for the simple reason that this guy is not matched in the usual arithmetic sense. So if you take my challenge, okay, and prove that every element of M is matched, that will immediately prove that this guy is not in M. Okay. Hard exercise. Okay, and this exercise is in the book. So if you choose to take this on, great. Okay, and then if you want to compare your solution with the solution on the web, fantastic. Okay. So hard exercise. Prove that all strings of matched parentheses are in M. Okay. So this is the other question. Remember, for example, we showed that every multiple of 4 is in A, and it was a more complicated proof with the well-ordering principle, and so on and so forth. Okay. So to prove that all strings of matched parentheses are in M, it's a more sophisticated argument, but you can try to do it. Okay. It's a different question. It's a very different question to asking, is everything in M, matched? That you can prove with structural induction. Structural induction is the tool to prove that everything in a recursive set has some property, not the tool to prove that everything with some property is in M. I hope you realize the difference between those two statements. Okay, more examples. Okay, let's do the speedy race. Bam! Okay, so structural induction on N. More examples. So remember the recursive set N, a formal definition of N. So, which is 1, 2, 3, and so on. So 1 is in N, and if X is in N, then, X plus 1 is in N. Okay. So let's consider some property that we'd like to prove of all the natural numbers. So for example, let's define a property P of N. So it's a property for the natural number N. It's the fact that 5 to the N minus 1 is divisible by 4. Okay. So I'm just claiming this. Oh, okay. So we have a recursive set. We want to prove that every element of N has this property. Structural induction. Step 1. Prove that the primordial ancestor has this property. So base case. So you can use structural induction for any recursively defined set to prove that, all the elements of that set have some property. Okay. Okay. So base case. So N equals 1. Okay. So P of 1 is the claim that 5 to the 1 minus 1 is divisible by 4. Well, 5 to the 1 minus 1 is just 4. 4 is divisible by 4? Of course. So this is true. It's true. Okay, so my primordial ancestor has the property. And now I need to show that my constructor rule preserves the property. So if, X has the property P of X, okay, so if X satisfies my claim, so that is, then, so this is the parent, then X plus 1 has the property P of X plus 1. So why X plus 1? Because that's the child. That's the definition of my set. This is the child. So in other words, this constructor rule preserves the property P of N, where N is my integer. So let's see if my parent has the property. So that means that 5 to the X minus 1 is divisible by 4. I need to show that the new child has the property. Okay, so what does this mean? This means that 5 to the X minus 1 is equal to 4K. Okay, it's divisible by 4. So this means that 5 to the X equals 4K plus 1. Multiplying both sides by 5. 5 to the X plus 1 is equal to 20K plus 5. Okay, subtracting 1 from both sides. 5 to the X plus 1 minus 1 is equal to 20K plus 4, which is equal to 4 times 5K plus 1. So it's a multiple of 4. So 5 to the X plus 1 minus 1 is divisible by 4. Okay. So if my parent has the property, then the child has the property. So the property P of N is preserved by the constructor. Okay. And so by induction, the property P holds for all N in my set. That's just a fancy way of saying for every N greater or equal to 1, 5 to the N minus 1 is divisible by 4. We've seen this kind of proof before. It's just regular induction. Induction is induction is induction. So structural induction, when the set that you're trying to prove all elements, so when the set that you're concerned with is the natural numbers, is just ordinary induction with this recursive definition. By the way, there are other definitions, recursive definitions of the natural numbers, and so you can, do structural induction on any valid recursive definition of the natural numbers. That gives you different forms of induction. Okay. Palindromes. Okay. Was it a rat I saw? Was it a rat I saw? Okay, that's called a palindrome. Okay, forget about the capitals and the spaces and so on. Was it a rat I saw? Going backwards, was it a rat I saw? When you say it forwards, when you say it backwards, it's the same. Okay, that's a palindrome. Well, we can let's focus on binary strings. Okay, so here 0 1 1 0 0. Okay, so that's a string. If I reverse the string, so we say that the reversal of this string 0 1 1 0 0. When you do the reversal of it, you just reverse it. You do exactly what we expect. You start from the back and go forward. So this is the reversal is 0 0 1 1 0. Well, this string and this string, remember, all that matters in a sequence, in a string. So those two strings are not equal. So we say that 0 1 1 0 0 is not a palindrome. Okay, not a palindrome. Okay. On the other hand, 0 1 1 0, that is a palindrome. Okay. So this is a palindrome. Okay, because if I reverse it, okay, so I start from the back and move. The reversal of this guy, so I use the superscript R. The reversal of this guy is 0 1 1 0. 0 1 1 0, which match. So these two match. Okay, so that means that it is a palindrome. Okay. So we can consider the set of all binary palindromes. Okay. Well, that's an interesting set. But let me now recursively define some set of binary strings. So let me call this set script P. Okay, is a set of binary strings. A set of binary strings. Okay, and 1. Tell me something that's in this set. Okay, now this is a case where I'm going to have 3 base cases. So far, we've only seen 1 base case. So 3 base cases. Epsilon, 0, and 1 are all in my set. Okay, so 3 base cases. 1, 2, 3. Okay. There are going to be 2 constructor rules. Okay. So far, everything we've seen. 1 base case, 1 constructor. Now I'm getting complicated. 2 constructor rules. Okay. If X, so X is in P, implies 0x0 is in P. That's constructor rule number 1. Okay. And there's a similar constructor rule where I can, so here I'm taking X and putting a 0 on the front and a 0 on the back. Okay, and here what am I doing? I'm taking an X. I'm going to take X. If that's in my set P, okay, I can prepend and append 1. So 1, X, 1 is in P. Okay. So let's see. What are some of the strings in P? Okay, what are some of the strings that are in P? So let's construct some of the strings in P. Okay, so P equals, we start with epsilon, 0, and 1. Now I can take anything that's in here and I can attach 0 to both sides or 1 to both sides. So let me take all of these and attach 0 to both sides. Well, if I take this guy and attach 0 to both sides, you get 0 epsilon 0, which is 0, 0. So I get, now in my first, think of this as the first generation. I get 0, 0 or 1, 1, appending 1. If I append 0 or 1 to this guy, I get 0, 0, 0, 1, 0, 1. If I append 0 or 1 to this guy, I get 0, 1, 0, 1, 0, 1, 1, 1. First generation. Now I can repeat. Okay, but observe that every string that was generated, okay, has every string that was generated is a palindrome. Okay, so claim. Okay. Every string in P is a palindrome. Let's prove it. Okay. Structural induction. Let's look at the base cases. So structural induction, base cases. In this case, base cases. Because I have more than 1. So let's do all the base cases. Well, these are all palindromes. So these are all palindromes. So just like the first orcs had blue eyes, my primordial ancestors are all palindromes. Now, I need to prove that the constructor rules, preserve palindromicity. Okay. So, prove that constructors preserve palindromicity. I don't know if I just invented a word. Okay, so prove this. Now comes the interesting new step. Well, because we have more than one constructor, we have multiple constructors, we have to prove it for every constructor. Not just, you don't just get to pick which constructor you want. We have to prove it for every constructor. So let's see. Okay, let's take a palindrome let's suppose that the parent is a palindrome, so 0, 1, 1, 0. So 0, 1, 1, 0. Okay, and what's the child? The child in rule 1 produces, add 0 on both sides, so you get 0, 0, 1, 1, 0, 0. Okay, and so the parent was a palindrome, the child is a palindrome. Okay, 2. Okay, you have 0, 1, 1, 0, and if you append 1, so that's the second constructor rule, you get 1, 0, 1, 1, 0, 1. Again, another palindrome, going backwards. In general, if you have a palindrome X, and you attach 0 on both sides, now let's see what it means to take the reversal of that. The reversal of that, okay, it means you start from the back and read towards the front. So you start from the back, you get 0. Okay, now you start reading X from the back to the front. So that's just X reversal. Okay, and then you end up with a 0. But if you started with a palindrome, X reversal equals X. So this is just X. If you start with a palindrome, then the reversal is a palindrome. So this is 0, X, 0 if X equals XR. That means that if you started with a palindrome and added 0 to both sides, you end up with a palindrome. You can make the same argument for if you started with a palindrome and added 1 to both sides. What am I arguing? I'm arguing that the base cases are palindromes and the constructor rules, 2 of them now. The constructor rules preserve palindromicity. That's what you need to claim by induction, more specifically by structural induction, that, this set that we constructed has all palindromes. Sorry, this set that we constructed, everything in this set is a palindrome. And now I leave you to fill in the details. So everything in P is a palindrome. Tough exercise for those of you who want the challenge. Prove that every palindrome is in P. That's the harder second kind of question. Everything that's a palindrome is in P. Prove. Exercise. So exercise. Prove every palindrome is in P. So in other words, this is a recursive definition of the set of palindromes. Everything in here is a palindrome, and everything that's a palindrome is in here. Okay? Let's do one more exercise. Arithmetic strings. Arithmetic string. So imagine, a set A of strings, and these strings are going to be made up of, parentheses, the digit 1, and addition and multiplication. So 1. The number 1 is in A. Oh, now we're going to view this number 1 as a string. And 2. There are 2 constructors. If, X is in A, constructs. So if you have something that's in A, you construct a string which is an open parentheses, X plus 1 is in A. Okay, so that's my first constructor. I can define any set I want, so I'm defining a set. Let's see what it is. My second constructor. If X and Y are in A, then in parentheses, X times Y is in A. Okay, so let's see what's in A. Well, 1 is in A, so A equals 1. And then now 1 is in A, so you get 1 plus 1 plus 1, and 1 and 1 are in A, so you get 1 times 1. Interesting. Okay, and now, since these 2 are in A, we can immediately get, for example, that 1 plus 1 plus 1
times 1, you know, is in A. Okay, and we can get that, you know, 1 plus 1 plus 1 times 1 plus 1 plus 1 is in A. So this is X, this is Y. Okay, and so on. So you see, it's generating arithmetic expressions. Let's evaluate these expressions in the usual way that we know how. So this is 1, this is 3. So we have 3 and 1 here. This is 3 times 1, which is 3. This is 3 times 3, which is 9. Okay. Looks like, you know, everything in here is an odd number, and indeed that's the case. Plain. All the arithmetic expressions in A, all the arithmetic expressions in A evaluate to an odd number. Okay, so let's see if this is true. Well, the base case is clearly true. Base case. Primordial ancestor. Base case. Clearly true. Okay. Now, I'm just going to show you that constructors preserve oddness. So constructors preserve oddness. Okay, I'm just calling this property oddness. Okay. And I said constructors because I have 2, so I have to show it for both of them. But let's see. If X is odd, so if the parent is odd, is that preserved in the child? Well, we have odd plus 2. So odd plus 2 is odd. So this rule preserves oddness. If the parents are odd in this rule, X and Y are both odd, then the child is the product. The product of 2 odd numbers, but the product of 2 odd numbers is odd. So this constructor preserves oddness. So the constructors preserve oddness? Yes. Now I leave you to fill in the details to prove all this, but that's all you need. That's the idea of structural induction. The primordial ancestors have your property, and procreation preserves the property. Okay? So, done. I've shown you the basic idea. Let's do a speedy race, and now come back and prove something about trees, okay? For which we gave a recursive definition of a structure. Okay? Wow! Okay, so let me remind you of the recursive definition of rooted binary trees. So R, B, T. Okay. And, okay, so, you know, the base case is the empty tree. So the empty tree is a rooted binary tree. Okay. And, you know, now comes the interesting case that if you have 2 rooted binary trees, T1 and T2 are rooted binary trees. And so what we do is we represent T1 and T2 sort of, you know, as these structures that look like trees. Okay, and they have roots, so these special guys which we call the root. Okay, then you know, when you join roots to a new root gives a new RBT. Okay, now it's important when I say that T1 and T2 are rooted binary trees, what we really mean is that they're disjoint rooted binary trees. So if you think about constructing a rooted binary tree with some people in here and some of those people also in here, then this definition doesn't work. These are disjoint rooted binary trees. So I mean, I don't need to say that. So all the circles, all the vertices, all the nodes in these 2 trees are distinct. So we use the word disjoint for that. Okay, so this means that the constructor rule takes these 2 guys and produces, you know, the following tree, T1, T2. So it's ordered. So the order matters. If you start with T2 and T1, you get the flipped version, the reversed version of this. And so that's a different tree in general. Now, these roots are no longer roots. Okay? And they both connect to the new root. Okay, so this is a new root. Okay, good. Okay, so this is the constructor. Now, okay, so let's have a look at some trees. Okay, so we've got epsilon. Okay, now this guy can give you, you know, just a root. Okay, and from this root, we can get, you know, we can add, you know, this guy can be T1 and T2. So from this guy, we can certainly get this guy. Okay. You put this guy as T1, this guy as T2, and connect them to a new root. And from this guy, we can certainly get, you know, we can make this T1 and this T2, and we can get a new root, okay, connected to this guy, and connected to this guy on the other side, okay. And if we wanted to, let's do one more. We can make this guy T1 and this guy T2. So let's see what that gives us. So it's going to be complicated. This guy is T1, so that's going to give us. This guy is T2, so that's going to give us. Wow, look at that beautiful tree. Woo! Okay, now what I want to do. Okay, so this guy is an empty tree. So, you know, it's not a very interesting tree. But, you know, once we get to the non-empty trees, let's look at the number of circles. Sometimes we call this the number of vertices or the number of nodes. The number of circles, and let's look at the number of links. So here are the circles. Okay, so nodes, or let's call them vertices. Okay, and links. Okay, so vertices here is 1, links 0. Vertices here is 3, links 2. Vertices here is 1, 2, 3, 4, 5. Okay, links 1, 2, 3, 4, 4. Vertices here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 vertices. And links 1, 2, 3, 4, 5, 6, 7, 8. 8. Ah, lots of nice tinkering. Okay. We should observe, if you have your tinkering hat on, that, look, the number of links is always 1 less than the number of vertices. Okay, even for this very complicated tree, this simple guy, okay, and that's in fact true in general. Okay. So every rooted binary tree, so everything that's constructed in this way, okay, as long as it's not empty, has a number of links which is 1 less than the number of vertices. So I'll claim every non-empty rooted binary tree has a number of links equal to number of vertices minus 1. So we're claiming a property of rooted binary trees. Okay, so structural induction, because this is a recursively defined set. I try to prove that everything in this set has some property, structural induction. So let's look at the base cases. So the base case. So is this property true for the base case? Base case. The empty tree. That's interesting. Okay, because this claim is a claim that requires a certain property of every non-empty rooted binary tree. So since this is empty, the claim is vacuously true. It's trivially true. Okay? Because this condition only needs to hold for the non-empty guy. Okay? So for the empty guy, you know, the claim holds. Okay? Now what we need to do is we need to prove that the constructor, the way of creating new trees, preserves that property. Okay? That, you can think of this as a property. So the next step, the induction step, okay, the way of creating new trees preserves, so I'm going to underline preserves. It's very important to sort of realize the importance of that word preserves. Okay, the way of creating new trees preserves the property. Okay, and we're going to consider 4 cases. Okay, of this of this constructor. Okay, so 4 cases. I'm going to show that the way of creating new trees preserves this property. And why am I considering 4 cases? Because, you know, the 4 cases depend on whether any of these parent trees are empty. The property holds for parent trees, but the parent trees are sort of special. If they're empty, they're sort of special. Okay, so 4 cases. And so let me tell you what the 4 cases are. So the 4 cases are T1 equals the empty guy, T2 equals the empty guy. So that could certainly be the parents, okay, that are going to create a new child, and these two parents have the property, vacuously, but they have the property. So I need to show that the child is a single node, and that that single node has the property. Well, in the single node is what we just considered here. Vertices 1, links 0, so check. Okay. Now, I could have the other two cases where T1 is equal to the is empty and T2 is not empty. Okay, and they satisfy this property. Okay, and the other case is that T1 is not equal to the empty tree and T2 is the empty tree. Okay, so that's the other case. Okay, and then the fourth case is where they're both not empty. T1 is not equal to empty tree and T2 is also not equal to the empty tree. Okay, so let's consider this case. Okay, so T1 is the empty tree. So what's the picture? The picture is like this. T1 is the empty tree, so you have the new root. The child that's created is a root that's connected on the left to nothing, but on the right, we have T2. Okay, what's the picture here? The picture here is the child. So I have to prove that this property is preserved. So we have the child, okay? And now T1 is not empty, so you have a real tree here, T1. Okay, but T2 is empty, so there's nothing on that side. And in this case, the child that's created has what's called a left subtree, which I'll call, which is T1, and what's called a right subtree, which is T2. But you don't need to, remember these names. I'm just showing you the picture of what's going on. Okay. So in all these cases, let's count up the number of vertices and the number of links. So the number of vertices is, so in this case, okay, the number of vertices is equal to, okay, 1, the new vertex, plus however many vertices are in T2. So it's 1 plus however many vertices are in T2. So let me call that, N2. Okay, so this is the number of vertices in T2. What about the number of links? The number of links is 1 plus however many links are in T2. So it's equal to 1 plus however many links are in T2. Let me call that L2. So L2, number of links in T2. Okay. But I know, so I know that the number of links, so I know that I want to show that the number of vertices is equal to 1 plus the number of links. Okay. So I want to show that 1 plus N2 is equal to 1 plus L2 plus 1. Want to show. Okay. Want to show this. So let's show that. So 1 plus N2 is equal to, but because this parent has the property, it's equal to 1 plus, so L2, N2 is L2 plus 1. L2 plus 1. Because the parent had the property. And if you compare this to this, you see it's exactly what I wanted to show. The number of vertices, okay, is equal to 1 plus the number of new links. Okay? So, in this case, I've proved that the property holds. Okay, so the property is preserved. Okay, what about in this case? Very similar. Let's count up the number of vertices. So number of vertices is equal to 1 plus N1. 1 plus N1, where N1 is the number of vertices in T1. Number vertices in T1. Okay, and how many links? It's 1 plus the number of links in T1. Number of links equals 1 plus L1. And the same argument, N1 is equal to L1 plus 1. So this is equal to 1 plus L1 plus 1. Okay, why? Because N1 is equal to L1 plus 1. The number of vertices in T1, because the parent has the property, is 1 plus the number of links. So 1 plus L1 plus 1. 1 plus L1 plus 1. But that's exactly 1 plus the number of new links. So the property is preserved. Okay, so the property is preserved. Is preserved. This is the most complicated case, so let's analyze that slowly. Okay, so let's just count up for the child. Okay, how many links and how many vertices? Number of vertices is equal to 1 plus n1 plus n2. 1 plus n1 plus n2. The number of links is equal to 2. So there are 2 new links plus however many there were in L1 plus however many there were in L2. So it's 2 plus L1 plus L2. Number of links in tree 1 plus the number of links in tree 2. Okay. So it would be great if this number of vertices is 1 plus that number of links. Okay, but we know that N1 equals L1 plus 1. N2 equals L2 plus 1 because we're only trying to show that the property is preserved. So we only need to consider the situation where the parents have the property. Okay. So what's the property? The property is that, the number of vertices is 1 plus the number of links. The number of vertices is 1 plus the number of links for both the parents. The number of vertices is 1 plus the number of links. Okay. In this case, here, this is 1 plus L1 plus 1 plus L2 plus 1. 1 plus L1 plus 1 plus L2 plus 1, which is equal to 3 plus L1 plus L2. So that's 1 more than the number of links. So the property is preserved. Property is preserved. Okay, so this has been a slightly complicated structural induction because it's involving a more complicated recursive definition of a structure, the rooted binary tree. What we have shown, the primordial ancestor, the base case has the property, and the method of creating new trees, okay, no matter what the parents are, as long as the parents satisfy the property is preserved in the child. That's all you need to conclude by induction, more specifically structural induction, that this property holds for all rooted binary trees. By induction, okay, for any non-empty rooted binary tree, the number of vertices equals the number of links plus 1. Fundamental property of trees, and we have proved it with structural induction. In any rooted binary tree, okay, you have 1 less link than vertices. Okay, so that's the end of the lecture. Let me summarize a little bit structural induction. Okay, so let me erase and summarize. Quick application of the result we just proved. Remember this tree I showed you last time? I'll draw it again. I drew this tree, and then I added 1 more link, and I claimed that this tree is not, this structure is not a rooted binary tree. And then we thought, wow, how could we show that? Because, when we want to show that something is a rooted binary tree, we give a derivation. To show that this is not a rooted binary tree, we have to show that no possible derivation can end up with this structure. Are we sure? There are so many ways to do derivations with that recursively defined, rooted binary tree, that definition. You can derive this way, you can derive that way. Are we sure none of them produce this? Now we have the tool to rigorously show that this cannot be a rooted binary tree. Okay? And, it's very simple actually. Let's count up the vertices. Number of vertices equals 1, 2, 3, 4, 5, 6, 7, 8 plus 4, 12 plus 3, 15. 15. Number of links equals 1, 2, 3, 4, 5, 6, 7, 8 plus 5 plus 2. Again, 15. Okay. But for every rooted binary tree, we just proved using structural induction that the number of links must equal the number of vertices minus 1. And in this case, that property is violated. This is not equal to the number of vertices, -1. And our structural induction proof is rigorous. So every rooted binary tree must have that property. So this cannot be a rooted binary tree. We don't need to consider all possible derivations. We have shown that it violates a property that all rooted binary trees have. That's the power of structural induction, to allow us to prove that property. Okay, let's erase this. And we'll be right back. Okay, so structural induction. It's very important for computer scientists. So is induction, by the way. And anyway, structural induction is induction is induction is induction. Induction is induction is induction. But structural induction is very important for computer scientists because, we build data structures. We build objects. We put them in memory. We run algorithms on them. Okay? And we want to prove that, for example, every structure that we built has some property. For example, when you talk about balanced trees, you want to show that every balanced tree has this property of balance, and so on and so forth. So it's fantastic that we build all these things, but it's even better if we can prove things about the things, prove properties about the things we build. Okay? And so structural induction is very important. Okay, so structural induction applies when you have a recursive definition of some set. So you have a recursive definition. Okay, so recursive set. Okay, now you have some property that you want to prove about all elements of the set. So you have some property. Let's call this set S. You have some property, let's call it P. You wish to prove about everything in S. Okay. So it's typical in a recursive definition. You have the primordial elements, okay, the base cases. So prove, you show P, you show your property for the primordial elements. These are the base cases in S. Okay, then you prove that, the way you construct new elements, the constructors, the way you procreate, prove that, the constructors. So the way you procreate, the procreation preserves the property S in the child. So this property S is inherited. Okay, so procreation preserves the property P in the child. Okay, that's created. Okay. And if you can show that, if you can show the primordial ancestors have blue eyes, and if you can show that blue eyes are inherited whenever the parents have blue eyes, bam! That's it, you're done. Okay. By structural induction, all the orcs have blue eyes. Everything in S has that property P. Important. I'll put it in red, and I'll put a big check mark. Structural induction is not for showing that everything with a property P is in S. Okay. So it's not for showing that everything with some property is in S. Okay. You need other techniques, well-ordering principle, and usually more sophisticated arguments. So structural induction can be used to show that all leopards have 4 legs. Structural induction cannot be used to show that all creatures with 4 legs are leopards. Okay. Structural induction can be used to show that all RBTs have, a number of links which is 1 less than the number of vertices. It cannot be used to show that all graphs in which the number of links is 1 less than the number of vertices is an RBT. Okay. And so on and so forth. So it's very important that you distinguish these 2 types of questions. So distinguish those. Very important that you distinguish those. Okay? So see you next time.